So we already heard about the smaller scales in the universe and how we can create life, and now we talk about the biggest stuff in the universe, so galaxies and dark matter. So before I start with that, let me just tell you how I got into astronomy. So when people ask me what I study, I reply that I study astronomy or astrophysics. I think there are always certain thoughts that come to people's minds. They might think that I'm really into Star Trek, that I watched every episode, or they might think that my parents gave me a telescope when I was 6 years old and I've been looking at stars ever since. Or they might think that I'm kind of a child prodigy and have been solving equations before I could even walk. But actually, none of that is true for me. I'm not so much into science fiction. I'm a theoretical astronomer, so I have not looked through a telescope until I was like 25 years old. And I think I was good in math when I was a small kid, but I really just more enjoyed playing video games and solving equations. So when I was about to decide for what to do for college, I wanted to do something with physics. And I think back then I was channeling my inner child. And when I was 6 years old, I really liked dinosaurs. It was at the time of the first Jurassic Park movie, and I could recall the names of a few dozen dinosaurs. So I think the reason why I liked dinosaurs was just because they were so big compared to humans. And so that's why I study astronomy. So let's first talk about size scales. And astronomers like to think in orders of magnitude. So they don't care about like factors of 2 or 3. So with that in mind, I think it's fair to say that most of the people here in the audience are around 1 meter tall. A meter, that's around 3 foot. And so dinosaurs can grow much bigger than that. They can grow up to like 10 meters. They get within a factor of 2 or 3. But we have to go much, much bigger. So if I ask you to name something really, really big, a lot of people will say, oh, what about the Earth? The Earth is around 10 to the 7 meters big. 10 to the 7, that means 10 times 10 times 10 times 10 times 10 times 10 times 10. You multiply 10 with itself 7 times. Okay, but let's go bigger. The Sun is around 10 to the 9 meter big. That's still 100 times bigger than the Earth. And we'll make a lot of those factor of 100 jumps in just a few moments. But just to show you what it means that something is 100 times bigger, use a size comparison of the Sun to all the other planets in the solar system. So this whole object here, this is the Sun, and these are all the other planets, and only this small one, this is the Earth. So it's really small. So we have to go much, much bigger. So the next biggest object we can think of is, for example, the entire solar system. If we count everything up until the orbit of our outermost planet, Neptune, we have around 10 to the 30 meters. So it's still 10,000 times bigger than the Sun. We're not even close to the scales that I'm studying. So if we were about to look for alien life on Proxima Centauri, we just heard about from William, we would go 4 light years. 4 light years is the distance light travels in 4 years. And that's around 10 to the 17 meters. So it's still 10,000 times bigger than the solar system. But it's still not enough. So to introduce the next scale, I just want to briefly talk about what a galaxy is. A galaxy, in the simplest form, is just an accumulation of stars and gas and something that we call dark matter. I will just talk about this in just a few moments. And so in our own galaxy, the Milky Way, there are several hundreds of billions of stars. So just think about that. So if we were to travel to the center of the Milky Way from our Sun, we would travel a distance of around 10 to 20 meters. We'll find a supermassive black hole in the center. But anyway, that's not big enough. Let's look at our own entire Milky Way. That's still 10 times bigger, 10 to 21, but not enough. If we go to the next most nearby galaxy, it's Andromeda Galaxy, that's 10 to 22 meters, but it's not enough. So what I study is something that astronomers, for some reason, I don't know why, they call it the nearby universe. And the nearby universe is everything within a distance of 10 to 25 meters. And as if you have if you lost track of the numbers, 10 to 25 is that number here. And I think it's called 10 septillion. 10 septillion meters. Everything was in that distance. Okay. So in 1930, a Swiss astronomer Fritz Zwicky, this guy here, he pointed his telescope at a galaxy cluster. A galaxy cluster is just an accumulation of individual galaxies. So he looked at the Coma cluster, this one. And he found something very peculiar. He found that those galaxies in this Coma cluster were moving very, very fast. So you were observing that those galaxies were moving with speeds of several hundreds of miles per second. So why is it peculiar? You know that gravity makes all objects attract each other. And we also know that the bigger the object is, the more gravity it has. And it also means that bigger objects have a higher so-called escape speed. The escape speed is basically the speed that a rocket needs to have to escape the gravitational field of the Earth. So the escape speed on Earth is around 10 kilometers per second, but on a smaller object like the Moon, it's only 2 kilometers per second. And so Fritz Zwicky was observing those galaxies moving very, very fast, but the system was stable, it was not flying apart. So whatever the escape speed in that cluster was, it was still higher than the speeds of those galaxies. So he was doing the following calculation. He was asking, okay, how much mass is there in this gas cluster that I infer based upon the motions of those galaxies? And he compared this to all the mass that there was based upon the stars and the gas in the system. And he found that there must be much, much more mass based upon the motions than what he could see. So he was very confused by that, but he concluded, okay, there must be some form of matter that I cannot see. So he called this dunkle Materie, which is German for dark matter. And so by declaring this kind of new matter component, he restored this balance between the motions and the gravity and the mass that there actually is in the cluster. So now you might think, okay, this was 80 years ago. But actually this picture still holds up. In fact, we now have very good evidence that the majority of mass in the universe is dark. And only 20% of all the mass in the universe is visible. It's made of all the stuff that you and me are made of. Electrons, protons, neutrons, quarks, all of that. The majority is just dark. And so nowadays our view of galaxy clusters is the following. There is a very massive galaxy in the center and a lot of smaller, less bright galaxies that all move around this massive one in the middle. And so this massive one we call the central galaxy, and all the smaller ones we call satellite galaxies. And what Fritz Zwicky was telling us was that in addition to those galaxies that we can see, there is also a large halo of dark matter, or simply a dark matter halo. So at this point, you might be asking, well, what is dark matter actually? Well, the answer that I will give you, that hopefully any other scientist will give you, is that we just don't know for sure what dark matter is. I can show you a picture of dark matter, but in essence, we just know that dark matter does not emit any light. And we also know it doesn't absorb any light. So for example, if we look into our own Milky Way, we can infer the presence of gas and dust because it blocks the light of all the stars that are behind it. But dark matter doesn't do that. It's simply invisible. However, Fritz Zwicky was telling us that it was producing gravity. So the leading theory, the most viable theory for what dark matter could be, is that it's some kind of yet undiscovered particle beyond the standard model. So in fact, astronomers believe that there's at least one other particle beyond the standard model, and it makes up the majority of the mass that there is in the universe. Okay, but that's not what this talk is about. My research is not about what dark matter is, but what is the relationship between galaxies and dark matter halos. And for my research, I use so-called galaxy surveys, which are basically dedicated telescopes that survey the nearby sky and note down the positions of all the galaxies that we can observe. So in my research, that is the slow-motion sky survey. So you can create these very cool maps here that I just made myself, and you can see each of those little points here in this map is a single galaxy in and of itself. And this is only a small fraction of all the galaxies that there are in the slow-motion sky survey. So in my research, I basically continue what Fritz Zwicky has been doing, but instead of using only a handful of galaxies, I use 500,000 galaxies. And I study how those So we can even create these really cool movies with SSS. Basically show you how it would look like if you would fly through the nearby universe. So these are actual pictures of galaxies. So you'll be a very massive galaxy cluster. So as I said, in my research I study how those satellite galaxies move around the big, massive central galaxies and how fast they move. And for example, we can not only infer that there is dark matter, but we can also characterize what is the relationship between galaxies and dark matter halo. Something that we, for example, find is that the satellite galaxies around more massive central galaxies move faster. This is what's shown here in this figure. So here's the brightness of the central galaxy, and here's the speed of the satellite galaxies. And because speed also correlates with the mass of dark matter halo, we can infer that brighter galaxies live in more massive dark matter halos. And so these kind of relationships help to inform our theoretical models for how galaxies and dark matter evolve over time. Because our ultimate goal for theoretical astronomy is to be able to simulate the formation evolution of galaxies from the Big Bang all the way to the present day. So here's a video that shows you a state-of-the-art simulation. And it shows the same simulation volume, but in different components. So here's gas, you can see dark matter, stars, magnetic fields, temperature, velocity. So it's really complicated. And so far we have not come up with a model that is able to explain all observations. But my research kind of helps to improve those models so that someday we'll hopefully be able to not only answer what is dark matter made of and how we create life, but also how do galaxies form over time. Thanks.
All right, so we're going to have our last few questions.
Does every star have its own solar system?
Oh, yeah, that's a very good question. So in recent years, we have been able to detect more and more exoplanets. So 10 years ago, there was not, the answer to this question was far from obvious. But nowadays, we actually believe that the majority of stars also have their own planets. And just think about how many stars there are in the Milky Way and how many galaxies we have in the universe, that adds up to a very large number of planets that there are in the observable universe.
What made you want to study galaxies?
Oh my god, that gets very personal, I guess. So, I think that there are still a lot of open questions about how galaxies form. There's still a lot of questions which are completely unanswered. So that's basically why I was so interested in galaxies as compared to, okay, there are also many open questions in exoplanets, but also just, it's really just because they're so big. I really like studying big stuff.
We had another question. If the sun is a star, why is it so different than other stars?
Different in what way?
Like, why is it bigger and different color than other stars?
Oh, okay, that's a good question. So stars are in some sense very simple. They can mostly be characterized just by what mass they have. So stars come in various sizes. So they can be like only half the mass of the sun, or they can be 100 times more massive than the sun. And the mass that they have also determines what color they have. And so you can mostly explain the variety of stars that you can observe based upon the variety of mass that they have. And the mass is just set by how they formed in the beginning.
My question is, what do you think people people would have a universe in the computer, basically? I think they'll react. What would they do with that knowledge?
Oh, that's a very good question. I think we're still a long way from there. And in principle, it would first of all be cool to be able to really have a model that's able to explain everything. From there on, we could ask, to actually get to this answer, we must also answer other questions, like how stars form, or how they form from gas, when do stars die, how efficient is gas, how efficiently is gas converted to stars. So by answering this question, we are also, in some sense, being able to answer all of other questions as well. So that would be basically the thing we would do. Basically, be able to have answers to various fields of astronomy by now.
All right, let's give us, okay.
Is it true that all the stars are the same amount of people?
Same number.
They say that each there's and one stars is like like we have 3 other stars. So is it true that all the stars with the same amount of stars in the sky is the same amount of people in Earth?
Oh, you mean whether So it is true that in the early universe without stars, there are very little elements other than hydrogen and helium. And so when stars, when they burn hydrogen and helium, and especially once they explode, they release all kinds of other materials, essentially the building blocks that you and we are made of. Is that the question that you were referring to?
Well, yeah.
Interesting how many stars there are.
How many stars?
Oh, just how many stars there are in the universe?
Yeah.
Oh, okay, that's much interesting. So in our own galaxy, there are around, we don't know exactly, but the order of several hundreds of billions of stars. And now there are still billions upon billions of galaxies in the universe that we can observe. If we multiply these two numbers, we come up with around 10 to 20 or more stars in the observed universe. So this is, again, a very, very large number. So if you're looking for alien life, you're probably going to find it somewhere.
Let's thank our speakers. If you have more questions that you didn't get to ask during the session, we're going to have breakout sessions. So Kimmy is going to be here in the auditorium, and if you exit and go to the left, there are 2 rooms. The first one is for Johannes, and the next one is for Lily. So you can talk to the speakers and get more stickers. You can also continue to ask other graduate students and postdocs here for questions so that you can get a prize if you haven't already, or if you want another prize. And if you also didn't get a chance to do the demos, you can do the